Thank you for showing up. We're here to talk about social microbes. 25 years ago, the scientists thought that bacteria were just single-cell, boring organisms that did nothing but divide and make more bacteria. But today we know that this is not the full picture. In fact, we're here today to tell you that bacteria are social. So most of you probably think about being social as something with hanging out with your friends and chit-chatting, and some of you may even play a game of cards with your friends once in a while. So what do I mean when I say that bacteria are social? Well, like you, bacteria like to hang out with their friends. But unlike you, they have thousands or even millions of friends. Bacteria also like to talk, but they don't chit-chat. When they talk, they're conspiring on how to launch an attack on the body that they live in. Bacteria also not always like to hang out with foreign bacteria, so they will pick up a fight with them. And finally, we're also going to hear something about how bacteria play cards, but we'll get back to that later. So we all know that humans cooperate, and a very well-known example of human cooperation is the tax system. If you think of the tax system as a way of providing common goods to the public, common goods such as roads and schools and hospitals and so on. So just imagine for a second if we didn't cooperate. There would be no one to build our roads and there would be no teachers at the schools, so basically we wouldn't have society as we know it today. So cooperation is good, but cooperation is also costly for the individual, and therefore there will always be someone trying to use the benefits without contributing. Those are called cheaters. And a concept known from sociology as tragedy of the commons tells us that if too many are cheating and enjoying the benefits but not contributing, the system will break down. So therefore, in a society where you have cooperation, you need to be able to punish the cheaters so that they will not cheat. And in fact, these social structures can also be found in bacterial communities. Bacteria cooperate and gain advantages that they would not be able to gain on their own. And they even have found ways to punish the cheaters. But let's get started. Now we will, during the next 4 talks, we will tell you that bacteria socialize and cooperate and talk and fight in all kinds of different environments, from the human body to decaying fruits. And we hope that we will be able to convince you that bacteria are in fact social. So the first speaker is going to be myself, and I'm going to talk about how the human pathogen bacterium Staphylococcus aureus is using social interactions to protect itself when it infects the human body. So last year, 250 people died from Staph aureus infection in Denmark. That is 5 persons per week, and this number actually exceeds the number of people killed in traffic. At the same time, 50% of the population is colonized with staph. So half of you will, statistically speaking, have staph in your nose or on your skin without knowing it and without getting sick. But once in a while, we're unlucky and we get a staph infection, and those can be very hard to treat, even with antibiotics. So why is that? So to answer that question, I'm going to take a small detour, and now I want you to imagine a battlefield at the time of the ancient Greeks. At this time, a formation of soldiers called a phalanx was invented. And in a phalanx, as shown on this picture up here, the soldiers stick very closely together, and they protect the group with their shields, and they can even fight off enemies with spears or other weapons. And if this formation was not broken, it was nearly invincible, and it was used to win numerous battles up through history. And the key word to success here was sticking together as a group. And that is the same keyword that the bacteria use when I ask you to imagine a phalanx formed by bacteria in the battlefield of the human body. Because in fact, Staphylococci are able to recognize its family members and get together in large communities as these clumps seen down here. And it's millions of cells which are glued together by a sticky substance secreted by all those cells. And this sticky substance not only binds the cells together, but it also functions as a shield to protect the community inside. So what are they protecting themselves against, the staff, when they're in these clumps? In the human body, in each milliliter of our blood, we have more than 1 million white blood cells. And white blood cells are fierce warriors trained to recognize bacteria, and they will very efficiently find and eat and destroy the bacteria. And they can do that because bacteria are much smaller than the white blood cells. So now what if the bacteria get together in large clumps as shown here? Then they cannot as easily be engulfed by the white blood cells, and they will have a harder time attacking the bacteria. But this is actually not the only thing that the bacteria have to worry about during an infection. Because if you get a staph infection, the doctor will give you antibiotics. And antibiotics have long been known as a miracle cure, saving millions of lives. And you have probably heard in the media that there's a growing problem with antibiotic-resistant bacteria. But I can also tell you here that even bacteria that are not resistant to antibiotics, when they gather themselves into these large clumps, then it takes 1,000 times more antibiotics to kill them compared to if they were living as single cells. So we thought in our group, what if we could disrupt these clumps? What if we could destroy this bacterial phalanx? Then the bacteria would be back in single cells, be unorganized, and they would be easy prey for both antibiotics and white blood cells. So in our group, we're working on finding out exactly how do the bacteria glue together and exactly how does that protect them against antibiotics and white blood cells. Because then we might be able to invent drugs which can now kill the bacteria more efficiently. Good. So this was about how to kill bacteria, but we may not always need to kill the bad bugs. Maybe we can just disarm them. So our next speaker, Mara, will tell you about how to sabotage bacterial communication. Thank you.
Thank you, Jakob, for the introduction. So, as Jakob already mentioned, bacteria... Okay, sorry? A bit louder, okay, thank you. So, bacteria are actually very social. And this is a concept that challenges the initial idea that bacteria are very simple organisms. They can't actually communicate with each other, and they're too small to make a difference in the human body or in the world. So, I would like to talk to you more about how we can, or how bacteria communicate with each other, but also how we can target this communication in order to be able to treat infections with bacteria. So, what happens when bacteria communicate, or basically when bacteria form together to become a group? They kind of change their behavior from a single cell to a group behavior, and they become more like a multicellular organism, kind of like what we are. And this is because they want to provide protection to the entire population from from antibiotics, or even from the white blood cells, or from anything in their external factor or environment. So before we can talk about how we can scramble communication, I need to tell you about how bacteria can actually communicate with each other, and how they know when to shift from being a single cell acting on its own to a group behavior acting in the population. And they do this because they can actually talk to each other using chemical words. And they do this using a phenomenon called quorum sensing. And quorum sensing happens only when there's a high population cell density. So what happens in quorum sensing is that when you have one cell, it starts producing these chemical words, but it's by itself. As the bacteria will kind of grow and divide and double, then they will all start producing these chemical words. And once they get to a high enough cell density, then they will start hearing these chemical words, and these chemical words will interact with the whole bacterial population and will cause them to shift their behavior from a single cell to a group behavior, and they'll kind of become like a community, like something that's sticking them together, and they'll be doing one thing to kind of protect their whole population and environment. And you can almost think of quorum sensing in bacteria as voting. So they vote with these chemical words. The vote will eventually get counted. They'll realize how many there are in the community, and then they'll all be able to act on these words and carry the vote out. So why is this an important factor, the quorum sensing in bacteria? Well, we know that a lot of group behaviors in bacteria are caused via quorum sensing. And this is how they are capable of interacting and living within, the environment. But there is one specific quorum sensing behavior that is incredibly important to us humans, and that is infection. We know that all pathogenic bacteria are capable of causing infection through the process of quorum sensing. So what happens is that if they're just by themselves, just this one tiny bacterium, as Jakob has shown you, this tiny thing, is too small to make any impact, and any signals that it might be, throwing out there will not be heard. However, if they start dividing within the human body, eventually they'll be able to sense that they have enough of them to launch an attack. And if they weren't able to communicate using quorum sensing when they get to a high enough cell density, then they wouldn't realize that there are enough of them to launch this attack on the human body. So now that we know that that's how pathogenic bacteria can actually cause an infection, we also know that we have a target. So we can target these chemical words in order to basically make the pathogenic bacterium either deaf or blind to these chemical words and to its own language. And we do that by introducing a language that is very similar to their original language. It looks the same, and it sounds kind of the same, but the sounds coming out they can't understand them. So basically what happens is that they can see the language, they can hear it, but there is no signal within the cell to cause these virulence to take over, to act as one group and to attack the immune system, the body. So what happens then is that we leave these bacteria who now are hindered. They can't actually function as a group because they think they're on their own. And that allows for the immune system to come and take over the role that it should do, which otherwise it couldn't do because the virulence factors will stop the body from being able to clear the infection. So why is this ultimately interesting? Well, the thing is that we have this problem of antibiotic resistance, and as Jakob also mentioned, especially with Staphylococcus aureus, all these kind of bacteria that are immune to antibiotics and causing infections, we need alternative ways to treat them when they do cause infections in the body. And one of them is to try and stop them, is to disarm them basically from causing the virulence factors, to stop them being able to communicate to each other that now we're enough, we can take over the body, and therefore we can treat antibiotic-resistant bacterial infections. So I spoke to you a little bit about how bacteria can communicate within a species, but they can also recognize self from themselves and interact with other species, and they can either do that by declaring war or actually forming alliances. And I will give you over to Martin now, who will talk to you about bacterial warfare in the human body.
Hello everybody. Now we have heard two talks about how bacteria can socialize in order to prevent from being attacked by white blood cells and antibiotics. We have heard about how they communicate in order to launch a coordinated attack on the body. Now this can sound that all of the bacteria are bad, but I'll try to convince you that not all of the bacteria are indeed bad. So we also have good bacteria in our bodies, and we are actually dependent on these bacteria to stay healthy. So if you take a step back and look at the average human body, this consists of trillions of individual cells. But for every time there's a single human cell, there will be around 10 microbial cells. So when looking at you, you are only 10% human and 90% bacteria, viruses and other microorganisms. But to our luck, the vast majorities of these microorganisms and bacteria are living peacefully with our body. And of the several thousand known bacteria today, then only around 100 of them are known to have the capability of making us sick. So why is it that we have bacteria in our body, and why are they actually beneficial for our health? So imagine if you come in as a single bacteria, and you meet these three guys, and these are part of our good bacteria in the body. So they have a nice place to live, they have plenty of resources so that they can generate offspring, so they are not willingly giving up this place for intruding bacteria. So not only are these good bacteria physically blocking the spot where the incoming bacteria wants to sit, they are also armed with weapons, so that they send out substances that will prevent incoming bacteria from having this place in the body. So we know that some infections only occur if we disrupt our normal flora, and so antibiotics that we use to treat infections, they cannot distinguish between who's the good guys and who's the bad guys in our body. So by treating with antibiotics, then we will swipe away everything, and now our body is more susceptible for incoming new bacteria. So what we can use this for is that if we can better understand how our normal flora is working, then we can use this to try to develop new therapies. And you should all be appreciating that we actually have bacteria on our skin, in our digestive system, and so on. And now, finally, our gambling professor will tell you a little about card games in the bacterial world.
So Mara and Jakob and Martin have been talking about social interactions of bacteria in various circumstances. One can answer how easy it is to predict how social interactions evolve. How does bacteria become friends? How does it become enemies? How do they ignore each other? And there you very often need models in order to predict what is going on. You can use two kinds of models. You can use the models like the weather forecast people are using, complicated mathematical equations, and then you can predict down the line what is going to happen with some kind of accuracy. But sometimes you don't even know what's really going on. There you need another kind of models. It can be games to identify which are the key players here among bacteria that are interacting with each other. And I will give two examples on that. The first one is not an example from our university, it's from an American group concerning complicated microbial communities. It turns out that in such communities there are a few species that are key species. If you lose those species, the whole thing will collapse. Why is that? They made a hypothesis based on the game of hearts called Hjertefri in Danish, where the loser is sitting with the Queen of Spades. Here we have a particularly nasty Queen of Spades. And actually, that's what's happening in these microbial communities. All the other species are losing some metabolic function that's important for the whole community because they grow faster if they don't have to do this work. So there are a few left behind that have to do this metabolic function that everybody is benefiting from, because if they also give up on it, everybody loses out. So this is the first example concerning metabolism and hearts. In our group, we are very much interested in antibiotics, and I'm going to talk about a specific kind of antibiotics called bacteriocins that are bacterial weapons some bacteria produce against other bacteria. Why do they produce them? Actually, they don't really know. One explanation has been that they are doing signaling to each other, waving flags with these antibiotics. Another reason is, they kill each other to be more in numbers. It's a number game. We think that the explanation is the third, that they kill each other to get the nutrients from these cells that are killed. They lyse, they are ruptured, they release the nutrients, and then the other bacteria that produce the antibiotics, the bacteriocins, can use these as nutrients. But there will also be resistant cells present that are cheaters, and they can also use these nutrients. So we have compared with a game of casino, where the target cells are sensitive to bacteriocins that matches the cards of the player's hands that the other players want to have. If you have broad spectrum bacteriocins, meaning you're inhibiting a lot of different bacteria, you can get more nutrients. In casino, that would be you're trying to make a build on the table. But when you make a build, you risk that actually other players are snatching the build just in front of you, and that are the cheaters. These are the resistant bacteria that are taking the game away from you. So we are using this analogy to go on with further work on see if this is really true. Is that why bacteria are producing antibiotics? Because if that is true, it also explains why antibiotic resistance is widespread in the environment. Because bacteria can get a benefit by being resistant. They get nutrients released by cells that are lysed by bacteria that are produce antibiotics. So these are simple games, rigid games. On a short term, they explain something. What about evolution? The games are changing all the times. You can have very complicated games like Uno, when turning the wheel decide what kind of game you are in now. But that is still a very rigid rule you are following, and in a way you can predict what is happening. So the real game is probably like Corvin ball, in Danish is stoffer game. You might not all be familiar with it, but I will read in Danish for you what it's about. Sten says, or Corvin says, andre spil er dødens pølse, dumme regler uden følelse. Stofferbold er meget bedre, alle burde klart det hedder. Ingen regler, ingen dommer, ligesom den danske sommer. And that is evolution in a nutshell, and if you want to do real models, this is the kind of games we had to invent. Thank you.
So thank you all for coming here with yourself and your social bacteria and socialize a bit with us. We hope we have been able to convince you that even though bacteria are not yet on Facebook, they are actually capable of performing social interactions. So we don't have time for questions right now, but we'll be hanging out at our exhibition down at the end with the small piglets. And if you have any questions or want to discuss, we'll be down there. Thank you.